Welcome everyone. We're going to start chapter 13 today, dealing with dealing with our vector functions and space curves. Okay, so now we're going to start to track some functions in 3D and get different equations for these particular paths of particles. That's kind of how I visualize it. And we'll get into our derivatives and integrals with that as we go. So we're looking at here. Our vector functions and space curve, our intro into that work. Okay, and so now what we're going to start to see is we'll find ways to write equations or functions to model or track curves in space, right? And so, of course, in 2D, we can have, right, our y equals some function of x squared, for instance. We can do like so, right? Or in 3D, what we can start to imagine, and again, drawing these out might take a little bit more thought and time. But now again, we're moving in three-dimensional space. So we might see, like, imagine our particle in movement going through space, weaving around, right? Rising, falling in that z direction, moving back and forth along our x and y. We can get this kind of space curve, right? And again, I kind of imagine like this particle traveling along its path, moving through space. Okay, but again, we can imagine that in 2 dimensions as well as we move along the trajectory. But we're trying to find our equations here. Okay, and so one method to write the equation or to track the location of that point along our curve. Right, so I'm trying to figure, okay, the path that this particle is following. At any moment, I can kind of track, okay, now my particle's here, then the point's this location, the point's at this location, same thing, right? First, my point starts up here, then as I graph, then it's going to move down here, the points I start to fill up, right? So I'm tracking that location, I'm looking along this curve. One method to write that equation or to track that location is to use a parameter, right? This kind of independent variable, t, right? Because a lot of times when we're talking about these, we're thinking physics, we're thinking about this particle. Where is it at this moment in time? Where is it at this moment in time? So on. This parameter t to create equations to find particular x, y, or later z coordinates along that curve, right? So again, thinking about, okay, when time equals 0, whatever it might be, I'm starting off my curve. Then when time equals 1 second, 2 seconds, 3 seconds, 4 seconds, we're kind of tracking that location. And even in this case, no one says that t has to be positive. We can say -2, -1, 0, right? It's just this kind of independent variable we're creating, this parameter, so we can start to track this location. And so, for instance, if we think about that y equals x squared, in some regard, we already have this equation, like x is a parameter, and then we can find that y. But for our parametric equations, we can recreate this and say, okay, well then, let's have x be equal to t, right? I can choose different values for our parameter t, and that'll be my x coordinate for my curve. And y is going to be t squared. Right, again, through substitution, if x is equal to t, then t squared is going to be x squared, and we're right back where we started, right? So it might not be that interesting as we begin, but it's this kind of concept that now, instead of having y depend on x, z depend on x, or z depend on x and y, we can create a new parameter, a new independent variable, and have our x and y depend on that parameter. So for whatever value for t, the singular variable, I can get a particular value for x, particular value for y. Okay, so now we had our parametric equation for lines. Now these space curves, similar idea. For any value for t we choose, we can plot when t equals 1, x equals 1, y equals 1 squared 1. So we get the order pair 1, 1, right? Equals 2. X equals t, 2. Y equals t squared, 4. Now we can do that for any t, and we can start to build up those order pairs and get that same curve we talked about before. Okay? And then likewise, we might get a set of parameters, right? Where x equals the cosine of t, y equals the sine of t, and then z is equal to t. Right, this is a common example. If that's a set of parametric equations for this space curve, okay, when we start to think about points, right, when t equals 0, for instance, then our ordered triple, cosine of 0, sine of 0, and then z is the same 0. So we're going to get this ordered triple. Cosine of 0 is 1, sine of 0, 0, 0. So we're getting this point. Then we can do another point, right? Like we could t equals 1, 2. Since I see my trig functions, we can incorporate some of those special radian values like pi over 2. You could do pi over 6, pi over 4, but when we start to see some fractions, radicals, decimal values, right, that would probably be a little bit more time consuming to evaluate and try to pinpoint, even worse, on a three-dimensional graph. But that same aspect, and even finding that pi over 2 on the z-axis can be a little bit daunting. But what we're going to see is here, cosine of pi over 2, 0, sine of pi over 2, 1, and that pi over 2 stays the same. We'll do one more here just for the sake of discussion, and I'll provide some helpful graphing tools online. So let's try again with now t equals pi. we're going to have cosine of pi, sine of pi, z coordinate is t, which is pi again. So now we're going to get this ordered triple. Cosine of pi, -1, so the x is -1. Sine of pi is 0 again. And then pi at 3.14 roughly. So we're getting these x, y, z coordinates for all these different values of t. We can go negative values for t as well. But when I start to put that on a graph, and we can do this on our graphing tool as well in just a second, I'll show. Right? If we start to work on this, make sure I make those negative. All right. But we're kind of identifying when t was equal to 0, remember we're at 1, 0, 0. So x is positive 1, y was 0, z was 0, so we're right out here. All right, so that's t equals 0. At t equals pi over 2, right? Half of 3.14. X is 0, y is 1, and half of 3.14, right? About 1.5, a little bit higher, right? Or up here. So that's going to be t equals pi over 2. Lining above if I can, that y equals 1. At t equals pi, right? So now the z is going to be up here at 3.14. Cosine pi, x is -1. Sine of pi, 0, y is 0. But now we're up z at 3.14, so there's t equals pi. So if we start to follow that trajectory, and this is where the graphing tool I'll show you is going to be helpful, what we're going to find is that our curve following this path is kind of arcing its way upwards. And we can continue. What we're going to find in this graph, again, a common example, is that as we continue, it's going to kind of continue to spiral around, and we're going to get a helix. Okay. The widest it'll go in x and y is +1, -1. I think about the amplitude of cosine and sine. The z is just climbing with t, it's just following what t is, so it's just going to stretch that, so like that spring stretching up. But along our path, for any moment in time, we can find our location going further and further up. Okay, and as I mentioned, putting that together, let's look at a graphing tool. So I'll put this link up on Canvas as well. But let me stop sharing here, share a different screen. And if I look at this window, this Calc 3D plot, we're going to deal with a space curve. Okay. So putting here, adding graph, space curve. And now we can see here, oh, it's going to make a fake one for us. So let's delete that. Okay. Depending on how far we want to go. But then x, recall, I had it as the cosine of t. Y was the sine of t. And z was just t itself. And we can range as far as you want, right? The number of steps, right? How many little values of t do you want to use? Okay. So there's our x, y, z. Graph in there. Okay. And as we start to go, again, I kind of try to orient here. You can see it starting off with that x is 1, y is 0. Sorry, try to tilt that better. Z is 0. And then as we start to regress, it's arcing its way upwards. Right, z is climbing, and you can start to see that bend going on. Okay, and again, we could incorporate here a higher value. see if that'll redraw for me. Okay, number steps, so we can make more. And again, I know it's stretched, so I'll probably have to go into my graphing, alter the scales here. Okay, but I don't want to spend time manipulating here. Okay, but again, probably with some of my settings, I could make it so the largest Z values higher to incorporate. Okay, and there's another graphing we can use as well, so right. And so another part of this, right, kind of getting into the other way we could visualize this is with a vector function, right? So kind of like we had done, let me stop sharing here. I'll come back to that in a moment. But here, another way to represent a space curve, okay, a location in space, is to use a vector function. Okay, and then this vector function identifies the location of the curve, right? Basically, or that particle on the curve for any parameter, again, t. And so what we're going to find is that we just kind of create this vector function, right? So my little arrow comes back, my then brackets, set of these, and now basically what I'm doing, I'm taking those parametric functions, the parametric equations, x of t, y of t, z of t, and using those to be my components of my vector, right? Similar, we can call it x of t I component, y of t j component, plus z of t k component. Okay, either one of those two. And so basically what we're kind of doing and we can put this back with our previous example, is that if we have some space curve here, this r of t is going to be like this vector that's from the origin pointing to whatever value, whatever x, y, z location we're at for the different times t. Okay, and so depending on what t, later on we can get that point, right? And we can use any value for t, a parameter. So it's just like we had done before, but now a little bit different notation, okay, for identifying. And so with that said, let me stop sharing here. Let's go back to this grapher, okay? And we can start to include, as it says here, right, this trace, okay? And I'm trying to get this a little bit better organized. There we go. There we are. You can kind of see our x, y, z, okay? And as we start to go through, I'm a little too fast here. You can see in blue here, sorry, in blue, is providing some other vectors that we'll talk about later in the section, okay? Let's see here. Don't need those, that's what that is. Right, so we're just looking at that R of t, that location. When t equals 1.2, we're here. Right? And so it's just tracing out for us that location for whatever value of t we're using. And it can go all the way up and through. So for whatever value for t we are, it'll point you to that location. That's what this R of t, okay, that space curve in vector form would look like. Okay. All right. And then there is another tool. Let's see here. Let me stop sharing there and switch over. We probably could have done it in the same screen. So it appears I'll put both of these graphers on the Canvas page. But if we type again, right, the cosine of t, sine of t, z was t, t can go from, there we can animate it, sorry, from there. So, graph, right, redraw display. And so there we go. And so this is going from that minimum t value -10, right? So there we are down here, -10 on the z-axis. Here's my x, y, z upwards. The biggest t, 10. Same as biggest t is going to be 10 for z as well. And we can see that helix, that spiral going, and we can animate. We can see kind of like that particle moving through. This one doesn't necessarily have that position vector pointing at it, but you can imagine that vector pointing at each of the locations for all the different values of t being utilized here. Okay. All right, stop sharing that. So again, we have this. Get back to my .cam. There we go. So for these space curves, right, we can either have our parametric equations, or we can represent that as a vector function, that R of t, cosine of t, sine of t, t, right? So again, x, y, z. And we can represent that function, that space curve, in this manner as well. Okay. All right. And so some minor points here. For our vector functions, we can compute limits right for that parameter component wise. So I can take this limit as t approaches a of this R of t to be the limit as t approaches a, right, of that x of t, y of t, z of t, or even using the I, j, k notation. And really we're just saying that we can push that limit through that vector function and just worry about taking those limits component wise. So if we want to see, okay, as t approaches 0, what is that curve, where is that particle heading? We can start to incorporate those limits. Okay, and it's our same limit rules and whatnot start to follow. And later we'll start to build that into, right, looking at derivatives. Okay, trying to find if this is the location of a particle moving through space, the velocity, acceleration, using those derivatives, right, which are all built upon the limit notation, right, building that way through. Okay, so there's our introduction to some of these vector functions, space curves, and we'll get into applications of these and some calculations as we further this discussion. All right, so take care. If you have any questions, let me know. I'll put those graphing tools in our Canvas page as well for you to access.